This Mathcast will walk you through section 11.1, where your students will explore how definite integrals can be used to compute the area contained by the graphs of one or more than one polar curve. There are two sections in Chapter 11 that are devoted to polar curves. This one, section 11.1, explores the ways that integrals can be used to compute the area contained by polar curves. And later, section 11.3 explores ways that derivatives can be used to find the slope of polar curves. Now, both of these sections rely on pre-calculus skills that were reviewed in section 9.4. In particular, your teams should enter this chapter ready to sketch polar graphs on their calculators or on paper, including circles, cardioids, and multi-petaled roses. They should recognize how parameters affect the shapes of these graphs, and also the domain on which closed curves can be traced out. They should also know how to convert a polar curve into rectilinear form. Lesson 11.1.1 will guide your students towards discovering a formula that uses integrals to evaluate the area of a region that is bounded by a polar curve. Now, this formula will be presented as the sum of infinitely many circular sectors. So we're going to start this lesson by reviewing in problem 11-1 how to find the area of a sector of a circle. So teams will work together in this problem to find a way to calculate the area of a sector with radius of 4.2 and a central angle of pi/6, and then they'll need to justify their result. So if you, as you circulate, see teams struggling to come up with a process to do this, you could suggest that they compute the area of a complete circle about this sector. This might help them visualize that the area of the sector is a fraction of the area of the complete circle. So, now that the process to find the area of a sector of a circle has been reviewed, problem 11-2 will challenge teams to use that area of a circular sector formula to approximate the overall area of a limacon. Now, before starting this problem, hand out resource page 11.1.1, on which your students will divide up the limacon into sector-like regions, each with a central angle, or delta theta, of pi/12. Now, as you circulate, be mindful about time. Of course, problem 11-2 is supposed to be a tedious problem, but you still do not want it to take too much class time either. So, as you circulate, encourage teams to find ways to split up the work. Perhaps they could divide up the sectors so that each team member will do an equal share of the calculations, and then they'll pool their results at the end. And also, encourage students to explore the natural symmetry of the limacon and thereby avoid redundant calculations. Problems 11-3 and 11-4 will guide your students away from the formula for the area of a generic sector of a circle and towards finding the area of an entire polar region. Now, be aware that these problems offer very little guidance, so your teams might need crafty prompting from you to come up with the idea to use limits to rewrite the generic sectors as infinitesimally small sectors before integrating. Now, to do so, they will need to let delta theta approach 0. But you do not want to directly suggest that they do this, as that would be doing the thinking for them. So instead, prepare pocket questions ahead of time. For example, you could project the definition of a definite integral in rectilinear form and ask students to explain the parts of this definition, noting how in this case, delta x represents the infinitesimally small width of each rectangle in the Riemann sum, and then ask them how a similar process could be applied to the variables of the generic sector. Now, after most of your teams have dawned on the corresponding integral expression that represents the area of a polar region, pull the class together and allow teams to present how they made sense of the equation that they found. Now, to check that their area formula actually works, problem 11-5, called Reality Check, asks students to use both geometry and calculus to compute the area of a circle centered at the origin whose radius is 5. And this will confirm that their formula does indeed work, at least in this trivial case. And then the area formula for polar graphs is summarized in a math note at the beginning of the next lesson, 11.1.2. This math note is followed by an opportunity for students to apply that formula on the very polar curve whose area they approximated during the previous lesson in problem 11-2. Now, the steps to evaluate this area are a bit lengthy, and without a calculator, these steps will allow for an in-class opportunity to review and discuss trig identities. Problem 11-16 explores the area contained by all 4 petals of the polar curve for r equals cosine 2 theta. After sketching this region, Part A will ask your students to determine all values of theta for which the graph passes through the pole. And there are 4. And then Part B will ask teams to interpret an integral expression that could be used to compute this area. Now, as you circulate, check in with teams to make sure that they understand that the setup in Part B illustrates a way to find that area using just one petal, the one between negative pi over 4 and pi over 4, and then quadrupling it. Now, finally, Part C will have teams evaluate that integral without a calculator. This gives you another opportunity to embed a review of trig identities into your calculus lesson. And in that spirit, the rest of the problems in Lesson 11.1.2 will allow your students to practice applying the area formula for polar curves and to discover, through discussion and through experience, the most efficient ways to set up these sorts of problems. For example, the area contained by the lemniscate in problem 11-17 can be found in many ways. It all depends on which bounds students choose to focus on and how they might want to exploit the symmetrical behavior that most polar curves have. So, as you circulate, attend to the different methods that different teams use and use study team strategies, such as the swap meet, where when a group is partially finished with the problem, one pair from each team will rotate to their neighboring teams and then share ideas, solutions, strategies, thinking, and then return to their original team to share what they learned. This will expose your students to more strategies to approach these sorts of problems. And continue to use the swap meet strategy during problems 11-18, parts A and B, and also 11-19 as well. This is a good strategy to use for all of these problems because there are multiple valid ways to find the area of each of these polar regions. And we do not want to dismiss or invalidate any team who goes about finding this area or these areas correctly. But we also want to ensure that students who were leaning towards a longer solution path get exposed to more efficient strategies as well. A clever way to start Lesson 11.1.3 is to project the integral expression shown in problem 11-27 prior to allowing your students to open their books, and challenge teams to sketch and shade the polar region whose area they think this expression represents. And you can use a think, pair, share for this strategy. Give students individual time to think about what this graph will look like, and then some more individual time to start sketching on their papers, followed by time to talk about it with a partner or with their team, and lastly, to share it with the whole class. After this amount of reflection time and discourse, most teams will produce a graph of a circle whose area is shaded between negative pi over 3 and pi over 3. Problem 11-28 adds a new challenge. In this problem, your students will be asked to calculate the area of this crescent moon-shaped region that is inside of one circle and outside of another. Like so many problems of this sort, there will be more than one accurate way to set up an integral expression that represents the area. But most of these ways involve calculating the intersection points on the diagram and perhaps the zeros as well in order to determine the bounds of integration. Again, there's more than one integral that can do this. However, that doesn't mean there aren't wrong ways to set up integral expressions as well. And problem 11-29 explores a common error that students often make in situations like this and gives teams time to discuss why this particular setup will be incorrect and if that was the strategy that they used in the previous problem, will give them the opportunity to revise their work if necessary. Your students will discover that problem 11-30 is trickier than it appears. Part A asks them to determine all the values of theta in which the graphs of a given cardioid and a given circle intersect. They will probably do this by setting the equation of the cardioid equal to the equation of the circle, and this will reveal two values of theta. Now, as you circulate, make sure that your students identify those theta values on the graph so that they recognize that there is a third location where the graphs intersect. That happens at the pole, where both curves have a radius of 0. Your students might wonder why the system of equations failed to locate this third intersection point. Now, the answer to that question can be revealed by evaluating each equation at r equals 0. Doing so will show that when r equals 0, theta will equal pi for the cardioid and pi over 2 for the circle. In other words, the point on the graph has a different r theta coordinate for each curve. Now, this is very important to discuss as you circulate because it addresses why this intersection was not found using the system of equations and why the area formula that they will write in Part C to find the area inside the cardioid and outside the circle will require the use of more than one definite integral. So this concludes our MathCast on section 11.1 on the area of polar curves. The next section, 11.2, will step away from polar functions and into how calculus can be applied to parametric curves and vector-valued functions. But we will return to polars again in section 11-3, this time looking at slope of polar curves.